Okay, so let's look into how this dilemma, the conflict between astronomy and earth science, got resolved. It took some luck and some hard work and the right person doing the work. So before we get into the details, let's talk about what has to happen for a breakthrough in science to occur. Because old ideas die hard, and the old guys are not always, but frequently are in the way. They've developed a prior generation of thought, and they're not going to give it up easily. Data is always under attack. Is it sufficient in quality and volume and timeliness? That's a challenge that new scientific theories have to face. And you always have, the outliers, people who want to discredit a new idea. So a lot of different people have to participate to cause this breakthrough that we're talking about here. Opinion makers frequently are specialists, but if you're working on a complex problem, an interdisciplinary approach is probably the necessary thing, an ingredient. And so you got to convince people in several different fields. We already talked about the data, the volume of it, and it's also one of the factors in the old professors impeding the acceptance of a new theory is they don't. If the old scientist doesn't understand the method, they have to be very skeptical, and these are complex things. You have to be able to differentiate between multiple phenomena. Prior theory was seen as one thing. So now we introduce Eugene Shoemaker. I've already mentioned him. He was became the authority in the field of impact cratering on asteroids and comets. And but the key thing was he had the right background to break this deadlock between planetary scientists and astronomers about the origin of cratering on Earth. He had background in planet science and rocketry, volcanism, but the key thing he had was he had worked on nuclear explosion craters, and that gave him insight into the dynamics that occur when a large amount of energy is deposited in the surface of our planet. So, lots of doubt, and nonetheless, Shoemaker and Baldwin, his collaborator, established that craters on both Earth and the Moon were created by impacts. There's Gene Shoemaker. So this crater is an example of the kind of thing he worked on in Nevada, a shallow underground nuclear blast. And this gave him the background to understand how to detect a crater caused by an impact or investment of a large amount of energy. And this related to the study of intense shock waves, which changed the structure of certain kinds of minerals. And that became a key clue in the connection between an impact, and the death of the dinosaurs. I'll probably talk about that in another lecture. So this was all done in the context of a nuclear blast. Very few events on Earth can create these modifications of minerals other than a nuclear blast or a big rock falling from the sky. So I talked about the fact that high-speed impacts will produce circular craters, not elliptical craters. And so there was new technology associated with high-speed cameras, so that these kind of cratering events could be watched at laboratory scale. Computer predictions, and we had this growing body of experience from nuclear tests, including this issue of how craters form when a large amount of energy is deposited in a geologic formation. And, as I said, formation of new rock types. And other fields of endeavor contributed to a growing body of evidence in the late 50s that cratering was common in the solar system, and why would Earth be excluded from that? Imaging got better, so that astronomers looking at moons of other planets could see circular craters, and remote sensing of Earth revealed cratering. Oil and gas researchers digging for oil and gas also were doing geophysical science and seeing a structure that had not been seen before. So we have a confluence by probably, I don't know, late 58, 59, an acknowledged expert endorsing an unpopular or mostly unproven idea, new measurement techniques, the fading away of the prior generation of professors and field geologists, inputs from other sciences like material science, and new vantage points. So we end up with a new approach. And this has its parallel in this idea, and what was an unpopular idea for a long time, continental drift, where you have this idea that large land masses have moved around and that Africa and South America had been part of the same object for a long time. So Shoemaker's contribution eventually convinced the community that cratering was common, that the oldest craters have been eroded away, and we now see only a few hundred surviving craters. So this at the start of this talk, I mentioned that understanding the history of how cratering was accepted as a theory of cratering based on comets and asteroids is how it emerged from a confluence of ideas. We have to think in terms of other science topics where this might be true. So there's this, has been a debate about the energetics of these hugely energetic objects in the sky, quasars, and Professor Arp, who thinks that the modern interpretation is wrong. At least at the time of my talk 15 years ago, he was still arguing loudly. Not much more has been heard from him. Infection as a basis of all disease. There's some evidence in that direction, but nothing conclusive yet. There's the famous story of ulcers, always thought to be the result of stress and bad diet, but a couple of young researchers in Australia show that it's actually the result of a very robust bacterium that can live in the human stomach and cause damage to the lining of the stomach. When this idea was introduced, it was treated with disdain, but the two guys that brought this idea forward and showed the proof ended up winning the Nobel Prize. There's occasional popularity associated with the caveman diet, arguing that the genome of modern humans prepared us for surviving in the environment 30 or 40,000 years ago, and that genome hasn't changed very much, and we should be eating like our ancestors did. And there's some diets based on that approach. Missing mass in the universe, the dark matter, that's a question that is unresolved. The existence of primordial black holes and the idea that they formed during the creation of the universe, and they could still be around, possibly in the neighborhood. and lots of others. Autism, multiple sclerosis, where the moon came from. These are all unanswered topics that need more attention, and the young people who want to become scientists are the ones who are going to work on these problems. So it's almost certain that in the next decades, scientists of that future date will look back and say, how could we have not seen the truth about some particular topic? It was right in front of them, like large land masses of, let's say, South America and Africa actually being part of the same landmass millions of years ago. You can hand a 7-year-old a pair of scissors and a map and see what they can figure out, and they'll quickly discover that South America and Africa look like two pieces of a jigsaw puzzle. But no professional geologist up until 40 or 50 years ago would have ever said anything other than it's just a coincidence. So even today, we have assumptions about the truth of our science, and a lot of it is wrong. We just can't see how to unravel those issues. And so all the future scientists who watch this have to be thinking deeply about how to prove the truth, even though there's a current theory that leads us in another direction. And these are questions I posed to the young people in the audience when I gave this talk, hoping to stimulate them to get into science and resolve some of these issues. And Gene Shoemaker was a multidisciplinary scientist, has to be smart and brave and patient, work hard, cover a lot of discipline, disciples, I guess I use that term there. Breakthroughs have to come from the integration of thinking, and Shoemaker also benefited from the time in which he was doing his work, the emergence of space optics and nuclear weapons testing, and new ideas for measurement in the geophysical realm from oil and gas industry, and astronomy, both in the ground and in space. All those things contributed to him being able to assemble a convincing story. And 1998, a lunar spacecraft carried a small part of his ashes after he had died and landed on the moon after the mission. This is something that Carolyn Porco, his friend and colleague, arranged for, and so she made sure that this inscription from Shakespeare ended up on the little capsule. Here's the dimension: 2 inches long and about an inch in diameter, and it's on the moon with his ashes. So there's tons of stuff on this topic. Here are a few examples of what you might go after, including this very interesting book, Thomas Kuhn's book on the structure of scientific revolutions. If you're interested in that topic, his is the book that really captured all the key ideas. And once